Here we are. Okay, so today's lecture. Up to this point, we've been talking about solving this, and we've spent a lot of time talking about this, and we've talked about some different ways to solve it. One is with the backslash command, another was with LU. Then we've talked about solving it with Fourier transforms. We've also talked about solving it with some iterative techniques. So, what I thought we would do today is kind of a smorgasbord lecture, well, where we talk about how does the Fourier transform work. There's some important issues about the Fourier transform that you have to think about when you build it. So I'll show you how to do it and how to take derivatives and things like this with the Fourier transform. We'll also talk about there's this matrix A that goes here, right? So when we write this as a AX equal to B, remember we constructed this matrix A in class and had a very specific structure. Well, how do you actually build it? You set up a nice way to build it. We'll talk about that using what are called the spdiag command, which is, this was a sparse matrix. We're going to build a sparse matrix. Okay? And then finally, how to use the iterative techniques such as GMRes and BiCGStab. So kind of an overview. This is real practical stuff relating to the homework. All right, so let's start off first issue with the FFT command and the IFFT command. Fast Fourier transform, inverse fast Fourier transform, and we want to learn how this works. Okay? Now, if you remember, there's this important result which says, this is the whole basis of why we use this. If you take the transform of the nth derivative, you get this result. Okay? So for instance, what I'm just going to do is just something simple. I'm going to take a function, find its derivatives. So all I really need to do to find the derivative of a function is just say, well, if I want to take, for instance, second derivative, what do? Well, I take the Fourier transform of the function I'm looking at, multiply it by this, negative ik squared in this case, and then inverse Fourier transform it. I'm done. Okay? So, but there's some issues here that you have to think about when you do such things. So let's go up here to the computer. Oh, one more last thing. The function we're going to actually look at to take the derivative of is going to be let's see. Eventually, what we're going to do is look at my favorite function, hyperbolic secant. Okay? Now, that's my favorite function. I don't know if anybody's picked their favorite function yet, but before you finish grad school, it's very important that you've at least thought about this issue and at least attempted to think about which one might be your favorite. Okay? It's okay if you've pared it down to 3 or 4 of them, but I've got mine. All right? And you can even pick mine if you want. I mean, it's not. I know this is a favorite function for many people. And what does it look like, by the way? If you haven't seen a hyperbolic secant, watch this. It's a bump. Turns out it's kind of an important bump for what I do. Okay, so here's what we're going to do. We're going to go ahead and start playing around with the Fourier transform to see how things work. So let's come up here to the screen. Start off the command lines with, your clear all, close all commands, just get things going. We have to define an interval to work on. 20. That's generic, completely random guess. And our interval, so the interval, let's say, will go from, x will be from negative L over 2 to L over 2. Okay? So we're going to make this domain go from negative 10 to 10. So 20 is the total length of the domain we're going to look at. Then, remember, with the Fourier transforms, I have to give it some number of points I'm going to cut this domain into, right? I'm going to discretize this thing, essentially. And how about 128? Remember, I have to pick a power of 2 here. 128 is good. 64, 256, 512. You pick something that's to the n. This is going to make the fast Fourier transform run in n log n. Okay? So now what you're going to do is say, okay, here's some commands that you may not be familiar with. What is my spatial domain then? I'm saying that I'm going to cut this domain up from -10 to 10 to 128 points. So let's do so. So what I can do, and it's going to be periodic, so the last point's going to be like the first point. So I want to do what's called Linspace Command, which stands for linear space. And what I want to do with this command, I want to go from the value of my x values goes from -L/2 to L/2. And how many points? n plus 1 points. Remember, the last point is like the first point. So I have n points I'm trying to solve for. The n plus first point is actually the first point again. So my total domain gets n plus 1 points. So this is all this command does, is make a linear vector that basically goes from -L/2 to L/2 in this many points. Now for solution purposes, one second real quick, for solution purposes, all I want, though, is the first n of those points. Okay? So, remember, I am cutting the domain up from, here's my first point, there's my last point. This point is this point because it's periodic. So all I have got to do is consider the points in between here. So if that's point 1, and that's n plus 1, I only have to keep these points around, with 1 through n points. And the n plus first point, I know what it is because it's just the first point of this. Okay? Everybody good with that? So I'm defining my vector x, which is going to be the first 1 through n points.
x2 is just a 1 by n vector.
x2 is a 1 by n plus 1 vector. X is a 1 by n. Yeah, so it makes a vector. So x2 is the vector with all these points. And then all I want is the middle one. So what this command here does, when we come to the screen, that just grabs the first 1 through n points of it. Okay? All right, so let's define a function. Let's start playing around with, before we get into our setch, a Gaussian, e to the minus x squared. That's also a bump, but it's not my favorite function, even though it looks a lot like my favorite function. It's a pretender. Okay? But here's a Gaussian. The reason I want to consider a Gaussian is because the Fourier transform of Gaussian is also a Gaussian. Okay? That's just a standard result that if you do the Fourier transform of Gaussian, you can actually calculate it explicitly out analytically, and you get another Gaussian. So how do you forget the Fourier transform of this thing? Let's call it UT for U transform is f of t, u. I have it now. Okay? So a couple things we're going to do here. First, let's plot. We'll do figure 1. In the first figure, we're going to plot x versus u. That's going to be the Gaussian. Okay, so let's do this first. Let's just run this code. Oh, by the way, yeah, let's okay, and we'll save this, file save as. Stuff. Okay, save. All right. You run stuff.m, and here's what it produces. There's a Gaussian. You guys can see that okay? Okay, a little bump. You can even make it bigger. See, there, that's fine. See? Nice little bump. Now, what you should do when you Fourier transform that is get another bump that looks a lot like this bump. And I've already written the code to do so, right? This is what the UT does. The UT gives me the other bump. So, in figure 2, let's plot that other bump. First of all, you get that. And you're going to go, whoa, what is that? Now remember, when you Fourier transform, you have numerical roundoff. And remember, when you Fourier transform, you have this e to the I. So when you have an e to the I, that means there's complex stuff going on. Even though you can work out by hand that it's supposed to be a Gaussian, there's no imaginary parts, numerical roundoff says, you know what, I can only keep the imaginary part down to 0 to 16 decimal places. So there is a tiny, tiny, tiny bit of complex piece here. And so what ends up happening when it plots this is because you are plotting this thing, what you really want to be doing is plotting the real part. Because there's a slight bit of imaginary part. So it doesn't know how to plot it. It's like, you want me to plot this, but I have a real and imaginary component, and so this is what you get. All right, so we'll fix that up. Come back over here, run it again, and voila, my new Gaussian. Okay, maybe that was too big. Okay, good. That doesn't look like a Gaussian at all. So what's going on? What's going on is what you're seeing is the artifacts of what makes the fast Fourier transform run. You're seeing the algorithm here. What ends up happening in a fast Fourier transform is you take your data, the data itself gets shifted, and then every other component gets multiplied by -1. So graphically, here's what happens. If you take this data and you Fourier transform it, well, the Fourier transform of it is supposed to be another Gaussian. But the Fourier transform takes this thing and splits it in the middle, crosses it over, so this piece goes over here, so that goes over there, this goes over here, so you get that. Then it multiplies every other point by -1. So this becomes, so if you follow the, so it looks like that. Okay? Why is this? Well, remember, I made this comment in class when we talked about fast Fourier transform, that one of the keys to making an n log n operation is the fact that you take a problem with n points, and what Cooley and Tukey did is found a way to take these n points and solve an n by n system of equations and say, actually, we can rewrite this as 2 n divided by 2 systems. In other words, 2 systems half the size. I can take this problem, decompose it to 2 systems half the size, and I can take that system, break it up into 2 problems half the size, and half the size, all the way down, so that what I solve is n 1-by-1 equations versus 1 n by n equation. Now, in the process of this factorization, this is what happens. The factorization process itself switches this and multiplies by -1. Okay? So this is an artifact of this fast Fourier transform, that it automatically does this. Now, when you have this shift, it's, you know, from some perspective, you don't really want that to be what you've got. What you really want to look is you know, you don't want to see this. So what you can do is you can say, okay, there's one more command. Let's say UTT. There's a command called FFT shift and IFFT shift. So FFT shift takes this and it goes, okay, it's shifted back to what it's supposed to be. Okay? So all you have to do is FFT shift UT. Then you can plot the real part of that and see what you get. There you go. Shifted it back. Every other component is still multiplied by -1. So you just say, okay, how about instead of plotting the real part, here, plot the absolute value. And there you go. So there's a Fourier transform of this. Gaussian, Gaussian. Okay? So these are technicalities because if you've done work with Fourier transforms, you know that it's supposed to be this sort of nice looking thing. And if you actually look at the output from FFT, you get this garbage, or what looks like garbage, and it's just a result of the fact that you have the shifting plus the multiplication by -1. So you have to take care of both those issues.
So is that always going to be the same? Like no matter what function,
No matter what function you put in, it always will do this to it. The nice thing about this is I know what it's supposed to look like. Suppose you take a function and you took its FFT and you didn't know this was happening, and suppose you had no idea what the Fourier transform was supposed to look like. You'd get this stuff and go, whoa, what's this? You have to remember that you have to make sure to understand that your FFT is going through this process. So that's why it's good to do the Gaussian, because I know what it's supposed to look like at the end, and so you can really see this process of what's going on to produce that right there. Okay. Now, here's the big deal about this. When we solve problems, all we really care about using the FFT is we're going to take data, we're going to FFT it. The thing we care about is that k vector. Because I have to, if I want to take a derivative, I have to multiply by this k vector. K is the wave number. So this essentially is stuff like cosine kx. Okay, so these are like our, I have a bunch of k's in here, and so it's like a Fourier series expansion. K could be 1, 2, 3, 4, 5. So I'm expanding the function in terms of a bunch of cosines or sines. Okay, fine. But now, remember, this k is this important, but look what's going on in this thing. Your data now gets shifted around. So your k values have to, you have to understand that when you do a FFT, you're going to be multiplying in the Fourier domain by the k wave vector, by this k vector. And the thing is, it's being shifted. The other thing that's being assumed when you do an FFT is that you're on a 2 pi periodic domain. Those are two issues that you have to take care of. This is not a 2 pi periodic domain. I took L to be 20. That's going from -10 to 10, which is certainly not 2 pi. Okay? So I have to take care of these two issues. And so, in fact, let's go ahead and do this. Let's go ahead and come back to this example. And now we're going to say, now that I've shown you this basic stuff, let's talk about calculating a derivative. Okay? All right. We'll do the same thing here, but now our function u is going to be my favorite function, sech. And I should mention that the derivative of sech is negative sech tanh. The derivative of, second derivative of sech is something like sech minus 2 sech cubed. So you actually can calculate these things analytically. So the question is, can I go ahead and do it here on the computer? Well, the thing that you need is, you need the Fourier transform. There it is. I have sech, and then I have Fourier transform. If I want to calculate the first derivative of this thing, I have to multiply the Fourier transform by negative ik, and then inverse Fourier transform. Right? Okay, so I need k, though. That's the big deal now. Here is k. First, it wants to be on a 2 pi periodic domain, and right now it's on a domain of size L. So you have to have the following scaling factor. This says, take my L, domain of size L, scale it down to 2 pi. Times my k numbers, which go 0 to n over 2 minus 1, and then minus n over 2 to negative 1. Now let me explain what I did here. What this did is basically took my k numbers, and the k wave numbers in the frequency domain start from 0 here, and they increase in value this way and this way. Okay, so let me draw this here. So by the way, my Fourier transform of a sech sort of looks like a sech again, and the wave numbers go from k equals 0 all the way to n over 2 and minus n over 2. I think it's actually n over 2 minus 1. So when you Fourier transform, you have n Fourier modes that go from Fourier mode minus n over 2 all the way up to 0, all the way to n over 2 minus 1. So what ends up happening, though, is when you Fourier transform, right, this thing gets shifted. This part goes over here. So look at the vector that you get over here. Well, now 0 is here, and it goes all the way up to n over 2 minus 1. And this part gets shipped over there, which starts at what? Then starting next to here is minus n over 2, and it goes all the way up to minus 1. So you have to make a vector that reflects this. The numbers in this vector go 0, blah, 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 all the way up to n over 2 minus 1, and then start at negative n over 2, go to minus 1. This is what I have done in this line of code right here. Start at 0, go to n over 2 minus 1, continue on it from negative n over 2 all the way to minus 1. This vector you need to use almost all the time. This is your k vector. This is your wave numbers. Very important. Yeah?
How do you define because k is a discretization on this domain. How do you define the decay, delta k? You know, like you say k is going from 0 to n over 2 minus 1. Like how many k's you have in there? I mean, how many different?
So how many k wave numbers? So remember, a couple things. What you're going to do is you're doing an expansion basically in terms of this is what you're really doing in a Fourier in a sines and cosines. You're doing an expansion of this form, and what you do, if you do it on a 2 pi domain, you know, if your domain then is from 0 to 2 pi, k takes on values of 0, 1, 2, 3. So k just goes from 0 all the way up to, k goes from minus n over 2 all the way up to n over 2 minus 1. Just integer values.
Oh, okay.
So you've scaled it down to 2 pi. This function is now periodic on an interval 2 pi because it's just cosine. So it's like cosine 1, cosine 2x, cosine 3x, cosine 4x, cosine 5x, all the way up to cosine, whatever you pick your n to be. So if you pick n to be fairly large, you get a lot, you know, if it goes all the way up to n over 2 minus 1. So if you pick n to be 128, this will go up to cosine of 63x. From cosine of negative 64x all the way to cosine, yeah.
The way you define the vector is going to be whole number, right?
Yes.
Okay, okay, only.
I have to find the vector. So the vector is going to be whole numbers, but then
you scale it by 2 pi, but what is inside this vector is whole numbers only, like inside the brackets.
yeah, this is only whole numbers in here, exactly. And then there's just the scaling factor
Okay.
to bring it down to a 2 pi domain.
Okay, so when you define the vector that way, it's going to be only, with MATLAB, it's going to be only whole numbers.
That's right, that's right. Yeah, so I'm going from 0 to this, and if I put the colon there, it does it in steps of 1.
Oh, that's what my question.
Yeah,
was.
okay,
Step
yeah.
by DK,
Yeah,
what
yeah.
is
So
the step?
if I wanted to change this, I could say go to 0 to 1 in steps of 0.5, I would do something like that.
Oh, I get it.
But if you do, the default is just steps of 1.
Okay.
Sorry, okay, there we go. So there's my k vector. So if I want to calculate the first derivative, let me call this ut1. So I'm calculating in Fourier transform space. So, and it's going to be to transform the first derivative is equal to, all I need to do now is say I times k, and k is a vector, times ut. By the way, I said that as minus ik. In the definition of MATLAB, the derivative is that. They use a different sign convention. Okay? So all I have to do is multiply by ik, take the Fourier transform, multiply by ik. There's my first derivative. You want to say second derivative? Just do square that, right? So that's going to be negative k times k times ut, so k squared. And the third derivative is, then you could just, you know, minus I times k. You could just do k cubed. There. And then you just plot it. Or actually, you have to inverse Fourier transform it now. So you can say my first derivative, let's do it right in the same line. My first derivative is equal to the inverse Fourier transform of ut1. And my second derivative is the inverse Fourier transform of this ut2. Oops. And my third derivative is just the inverse Fourier transform of 3. Okay? And I even gave you an example in the notes that I plotted the exact solutions along with them so you could see how accurate it is. I won't do that here. So now you can say, okay, let's plot these. So let's plot the function u. Let's plot its derivative. And by the way, so we'll plot the function. We'll plot its first derivative, plot its second derivative, plot its third derivative, and we'll run it. There you go. Blow this up. So the function is right here, the blue line. You can't see blue probably on the screen, but it's the one, its first derivative is this one here. Second derivative is this one right there. Something's a little off. Hold on a second. Don't I give a picture of this thing somewhere? Probably not. Notes. So do the first, second, third derivative. I'm missing a... So... I think it's all right. Okay, sorry, that was right. Okay. So anyway, those are your derivatives of this thing. Okay. Mm-hmm.
I'm sorry, but you don't have to shift it this time because you just you use the key vector.
Remember. Okay, so why didn't I have to shift it this time? The reason I didn't have to shift it this time is because remember, when you take the FFT, it shifts it. But the inverse Fourier transform already knows that it's shifted. So you remember here, we're using the pairs. We're Fourier transforming, then we're inverse Fourier transforming. So the inverse Fourier transform already knows about this. So it says, take this thing that's shifted, and when I undo it, pull it back out. So the only thing you're responsible to do is make sure that you're aware of this so that when you build this K matrix, the K matrix, or K vector, knows that this thing is shifted. Yeah.
So you shift and try to inverse it, that'll screw it all up?
Yeah.
Okay, and also...
Yeah, so in fact, you don't want to use FFT shift. The only reason you want to really use FFT shift is if plotting the spectrum is important to you somehow. Does that make sense? So like, I want to look at the spectral content, see what's going on in the frequency domain of this thing. Well then, to make anything reasonable out of that, you've got to shift it so that it looks like it's supposed to. That's the only reason you use that command. Okay. But that's important in things like, for instance, when people look at turbulence, all they care about is spectrum. All they care about is what's going on with the wave numbers. Well, in that case, you don't want to be plotting it shifted and multiplied by -1. You want to actually plot what the spectrum actually looks like. Okay? So that's how you do derivatives. Part 2. Let's move on. So that's a little code for doing stuff. Okay? And I'm going to go ahead and erase it. It's all in the notes, so you can download it from there or look at it. The next thing we want to do now is then say, okay, so this is the details of using this FFT and IFFT. You have to be aware that this is an issue. So this is the piece of code you need to help you out with that. Now let's come back down to this AX equal to B, which is, if you remember the form of this thing, in fact, the form of this thing, you can see it on page 37 of the notes. We did it for the case where we were looking at this matrix A, which kind of took on the following form. Had -4 down the diagonal, 1's down the off diagonals, but every nth point there was a 0. Same thing here. So anyway, if you look at the structure of that matrix, then there were some 1s over here, some 1s over here. Then opposite this 0, there was a 1 over here every once in a while. And then over opposite this 0, there was a 1 up here. And then finally 1's over here and 1's over here. So that was kind of the structure of this matrix. Just take a look at it there if you have it handy for yourself. On page 37, I wrote down what the matrix looks like. This is what you get when you take this operation, which is 2 derivatives of x and 2 derivatives of y. The Laplacian 2 derivatives of x, 2 derivatives of y, when you discretize it, second order accurate in x and in y, it actually produced a matrix that sort of looked like this. Now, the important thing about this is, basically, there are not that many diagonals here that matter. If I make n really huge, I'm still left with the same diagonals that matter. There's 9 of them. So 3, 4, 5, 6, 7, 8, 9. Okay? Only 9 diagonals I've got to build. Everything else is 0. So, one of the things that MATLAB allows you to do is to build these sparse matrices. Sparse meaning there's not that much actually on them. It's mostly zeros except for a few diagonals. There's 2 advantages to using sparse matrices. One, MATLAB stores a lot less of this thing, so it takes less memory. So when you have a really large matrix, instead of storing, if this is n by n squared amount of data, all I have to store is 9 diagonals, so it's 9 times n. So your storage is a lot less, which means your number of calculations is going to be a lot less also. Okay? So that's what the sparse matrix does. How do we build it? Well, I have a little code in here. And what we're going to do is we're going to do n equals 5. So we're going to 5 points in this direction, 5 points in this direction, x and y. Now remember, if I have 5 here and 5 there, the size of this matrix is okay. So there's that many rows, that many columns, m squared. Okay, so let's just make it as an example for something we could see. So my size of my matrix will be that. Okay? So this is the operational size. Now, notice a couple things. Mostly what I've got going on here are 1s that I've got to put in these diagonals. These diagonals here are mostly zeros with an occasional 1. So I'm going to define, the way this SPDiag works is what you do is you define, let's define a vector.
Can you just come to the right for just a second?
Am I right?
Yeah.
Is that good?
Yeah.
All right. Is that good? Okay.
Got it.
All right. Okay. First I'm going to make, oops. Hitting the shift key. Okay. I'm first making a vector of zeros right here. What size is it? N by 1. It's a column vector. Then I'm going to make a vector of 1s, which is size by n. And the reason I do this is because these are going to be what I'm going to fill in here. These diagonals are going to be full of 1s or zeros. Okay? And bear with me. I'm going to have a bunch of these rows, so I'm going to make some copies of them and call them something else. And the reason I'm going to do this is because now what I've got to do is I want to make these 2 vectors. I want to make this vector here, which, notice, at every nth point, I have to have a 0. This is due to the periodic boundary conditions. If you go back to the calculation, that's why we have zeros every nth point. I got to go put those in. Here and here. This one is almost all zeros, but every nth point, I have to put a 1 into it. Also a result of the periodic boundary conditions. So these two vectors, I want to define them. One of them is all 1s and every nth point is a 0. The other one is all 0s, every nth point is a 1. So this is what these vectors E2 and E4 are going to be. So I want to go down this thing, all the components. And what I want to do is, or every mth point, I want to say that E2 m times j is equal to 0. And E4 m times j is equal to 1. Notice it's an m by m is the length of this vector. So E2 says, okay, for j equals 1, go to the mth component, and this, remember, is a bunch of 1s, put a 0 there. And when j equals 2, go to 2m, put a 0. J equals 3, go to 3m. In other words, this is what I'm doing. This is m, 2m, 3m, 4m, 5m, putting in zeros. The vector that's there is supposed to be a bunch of 1s, and I'm just putting in zeros there. E4 is the opposite. E4 is a bunch of zeros to begin with, and what I'm doing is same thing. mj, put in a 1. So in other words, if j is 1, go to the mth component, put in a 1. If j is 2, go to the 2mth component, put in a 1. So now I'm doing this one. 1, 1, 1, 1, 1, every nth component. Okay? The other thing you have to worry about is if you look at that matrix carefully, this set of 1s and this set of 1s are shifted slightly. Where that one is and where this one is slightly different from where this one is. This is like one below it. If I were to draw it, it's like down here by 1. So they look like the same vectors, except for this one's shifted a little bit. Okay? So I'm going to shift these things. I'm going to create two new vectors. Same thing happens, by the way, between these two. This zero is up one row from that 0. Okay? Again, relies a lot on the structure. You have to study 2.1.13, that equation there, that matrix, carefully to see what the structure is. But what we're going to do is we're going to reproduce it with this spdiags command. So my matrix E3 will be something like this. Watch what I do. I basically rip off what I'm doing with this E3 command is I'm shifting everything by 1. So E3 looks like E2. E2 is a matrix with a bunch of 1s and a 0 every nth point. And what E3 is this same matrix, but notice what I did. I took all the E2 components, the first 1 to n minus 1, and I'm saying that those 1 to n minus 1 now are the 2 to n minus 1. Oops, sorry. This should be 2 to n. So I shifted it all up by one thing. So I took all these values, I shifted it up 1, and then the top one I'm going to put at the bottom. That's what this command does. Okay, that's all it's doing, is a shifting. Same thing with E5. Oops, all right. Shift it all up 1. And then 1, 1. Shift the last one down. So this is now your other one. There. Okay, now I'm ready. Because what I've done is, at this point, is I've built all these things. I have negative 4s here. I had to build this vector and this vector. This vector I built, and then I built the other one by shifting it. I built this vector, and then I built this one by shifting it. Now I just have to place them in there. Where do they belong in this matrix? Okay? So what the spdiag command allows you to do is put these things in. And here's how it works. My matrix A is equal to spdiags. And the way this equation works, or the way this thing works, is you say, in this here, You have to get a set of information. And this is the basic structure of the thing. You tell it what size matrix you want. I want an n by n, right? There's n rows, n columns. And then what you do is you tell it what you want in those diagonals and where the diagonals are placed. So what goes here will have some corresponding placement there. This is what these two boxes are for. So for instance, if I wanted to put -4 all along the diagonal, what I would do is say, I want -4. So I'm just multiplying by E1, which is 1s. And I want -4 times E1, and I want to place it on the diagonal. The diagonal is the 0 spot. So this is 0, 1, 2, 3, 4, 5, -1, -2, -3, and 4. So you can tell it which diagonal you want, centered on here. What do you want to put on there? I want to put -4 times a bunch of 1s. So what this does would create a matrix which has a bunch of -4s on it. Let's actually take a look at that real quick. So if I run this, I'm going to create it. And then I'm going to teach you this cool command called SPY A. It looks at the structure of the matrix. It basically tells you all the non-zero components in the matrix. So watch this. Do this. There. So what the SPY A command does, how big should this matrix be? I picked n to be 5, so this should be 25 by 25. And it is. And what happens here is, notice, basically what this is a visual representation of your matrix. The blue points tell you the components of the matrix that have non-zero component. The only one that's non-zero component is the diagonal. And you say, oh, look at that. Well, what is it, in fact? Well, for instance, A11 is equal to what? What is it equal to? -4. This is like I built it to be, right? All right. So now what we need to do is put in all these other things we have. So let's start here. I'm going to build it this way. I have E1, E1, this matrix here, which is the one with the 1s every nth point. This matrix here, which is 0 every nth point, -4, and then followed by E1s over there. So actually what you get is the following. This is going to be E5, and I'll let you study this more at your own leisure after class. So here I go. I'm going to put rows of 1s, a row of 1, a row of E5. And remember, E5 is related to this E4, which is a 1 every nth point, otherwise it's 0. E2, which is 1 everywhere except a 0 every nth point, followed by -1 on the diagonal, followed by, now I'm going to have E3, followed by E4, E1, and E1 again. By the way, to continue a line in MATLAB, you just go dot, 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 and then return. That means the next line is a continuation of the one above. And where am I putting these? Let me put this down. I'm going to let you think about it, because we don't have enough time to... building this matrix is very important, but it's also very time-consuming, unfortunately. Okay. Is that right? I think that's all I've got. So I have 0. I have two diagonals at -1 and 1, which are these two, and then m minus 1 and m plus 1 over. I get the other ones, and then minus m and plus m, and then further over from that is m by n, and that's all you need. So now, when you do this, you get that. That is the structure of the matrix you'll be working with. This matrix here takes 2 derivatives in x and 2 derivatives in y when you multiply it by some function, by some vector. This is your data. Partly why I build it in class is because you can see it's kind of a harder thing to do, so I give it to you. you have to build matrices B and C, which is closely related to this. So you're going to have to still work out the calculation, build this thing up. But the idea is, with this command structure working, okay, and with the stuff you have, you can spend the time to go through and figure out how to do this. I mean, this is very important in the sense that once you build it once, that's all you need to do. But you have to go through the work to actually figure out, what does it mean for me to take two derivatives in x and y? It means this, and it creates that matrix right here. And now the beauty of it, too, is here's the structure of it. And you want to make a bigger matrix, you can pick the number of points you want to do right here. I want to chop up 100 points in x and y. And also you do this, now you get this huge matrix. See, like I'm running it, and I think I'm running it. Okay. How about I'm going to make this huge matrix. Usually it should say busy. Did I do something wrong here? Anyway, we'll see if something pops up in a minute. That's odd that it didn't. Because it usually says busy if it's still going, but it didn't that time. But this allows you just to construct a matrix of arbitrary size. Once you've got the pattern down for it, and everything is scaled in terms of n and m, I can say, I want 200 points in each direction. It'll build the matrix for you. Okay? So this matrix is really nice because it's fundamental in the sense that two-dimensional problems, taking the Laplacian is a standard thing to do. So this matrix you carry around with you. And it saves you space. You can manually go through and put in, make a big matrix of zeros and randomly put these things in, but then this is actually only has 9 diagonals with, so 9 diagonals for n by n, so you only have to store 9 times n. Okay? So think about that piece of code for a while, because that one's going to be very important. And you're going to have to create B and C. So it's based a lot upon this. Final thing. Again, related to what we want to accomplish. For the iterative methods, for solving ax equal to b, 2 commands we're going to use specifically for the homework. gmres by cgstab. gmres is a generalized method of residuals. BiCGStab is biconjugate gradient stabilized method. And in its most simple implementation, you would just say, if I want to solve this, all I have to do for either one, just go like this. Replace that by BiCGStab for the other one. Simple as that. Give you a solution. But I'm not going to make it that simple for you, because there's a lot more here to be got. If I want information, like for instance, did this converge? Did it, in fact, can I adjust the tolerance I want for the convergence? Can I give it a guess? Remember, this is an iterative method. It's going to just iterate to try and find a solution. Well, what if I know the solution, or kind of nearby what the solution should be? Shouldn't I put it in as a guess? It should converge quicker. So the general way to do this, for instance, for BiCGStab, is this. And then let's put, I'm continuing that line. And just check out this. There's a bunch of options you can do here. This is a pretty fancy you can use a lot of options if you want. You give it your A and B, called gmres. You can tell it when you want it to restart. You can tell it what tolerance. You can tell it don't do more than this number of iterations. So you can increase the default or decrease it. You can use preconditioners for the matrix, which we're not going to deal with. If you don't want to send anything into any of these things, you put that. That means use the default. So if I want M1 and M2 here, just put in these empty boxes. You have to put something there. And X naught, your initial guess. So for instance, when we're solving the stream function, we're updating in time. Remember, once you've solved the stream function the first time, you say, well, I've solved it once, and as I take a step forward delta t in time, my stream function doesn't change that much, a delta t into the future. Use your previous stream function then, or vorticity, to help you solve for this. That should be your guess. Okay? And then what's going to give you out is your solution, a flag, and you can look what the flag means, but flag 0 means, flag is 0, that means it converged. Relative residual, how quickly is it converging? So with relative residual says, AX equal to B, this is supposed to be solved. So what it says is, what's the value of that? It's supposed to be 0. If it's not, what is it? So it tells you how far away you are. And the number of iterations it's taking to solve for this thing. These will all be important because it asks you very specific things to do with them in the homework. Okay? All right, more details about homework 2 and some of the computational issues on Monday. Have a good weekend. Office hours today, 2 to 3:30.